Right. Hello everyone again. Welcome to the evening public lecture series. So our research school, Quantum to Cosmos, Ideas and Applications. So this evening we have Tracy giving a talk to us with the title Light from Darkness, Searching for Dark Matter in the Sky.
Well, thank you very much to the organizers for the invitation, and thank you all for being here. This is my first visit to Istanbul, and I'm really enjoying myself. So I will, this evening, try to tell you about, well, first to give an introduction to the puzzle of dark matter, although some people in this room are pretty familiar with this puzzle by this point, and what we think we know about it, what mysteries remain open, and how we might try to better understand those mysteries by looking at observations of the bright part of the cosmos. This background image is an estimate of what the dark matter halo looks like, overlaid with an image of bright high-energy photons streaming at us from the center of our Milky Way Galaxy. So I want to begin with the dark side of the picture. And yeah, how many people have seen Star Wars in this audience? Do we have good Star Wars penetration? Very good. Okay, my jokes will not completely fall flat then. So I first want to talk about, I spend a large amount of my working life thinking about this question, what might dark matter be? How can we figure out what it is? How can we figure out how it behaves? So I want to first lay out for you why this is a problem that's worth thinking about and what we currently know and don't know. Then I want to switch over to the light side and ask about why should we look for visible signals of dark matter in light? Why is this a sensible thing to be doing? And I want to show you an example, which is looking at the sky in the highest energy light that we can see, gamma rays that have energy that's billions or trillions that of the light that's shining on us in this room. And I'll show how that has unveiled several mysteries at the heart of our Milky Way Galaxy, which are may be telling us about dark matter, but are probably telling us about the deep history over the last billions of years of our galaxy. Okay, so let's begin on the dark side. So here's what I'll tell you that we think we know about dark matter, and then I'll give you some background for why we think that these things are true. We believe that it's roughly 80% of all the matter in our universe, stuff that you learned in school, that some of you have learned in school and some of you will learn in school, about matter being made up of protons and electrons and neutrons. That's only true for about 20% of the matter in our universe. The rest is this other stuff that we don't understand by mass. We know that the dark matter has mass, and hence that it gravitates, but as far as we can tell, it doesn't scatter, emit, or absorb light at any level that we can yet measure. So really, dark matter is a bit of a misnomer. This is really transparent matter. Light should just flow straight through it. If it interacts with other particles, except by gravity, it does so only pretty weakly. However, a lot of what I tell you about this evening is going to be trying to find the traces of those weak interactions, because if they're there, they could give us a huge amount of information about how the dark matter behaves. And the last part, and that what tells us that this is a puzzle, is that the properties that we do know are already enough to tell us that none of the particles that we know about provide a particularly good candidate for it, with a possible exception for if the dark matter is entirely made up of little black holes about the mass of an asteroid that were formed in the very early universe. So the open questions: what's this stuff made of? Are we talking about a new particle? Are we talking about many new particles? Are we talking about twisted space-time? Are we talking about tiny black holes formed in the universe's first instance? Where did it come from? Why is it 80% of the matter in the universe? What created it? What destroyed it? How does it interact with ordinary particles? If so, how do those interactions behave? We know this very well for particles that we can measure and that we can produce at colliders. We don't know this answer for dark matter. And I could keep listing questions like that for quite a long time, but that's not the most interesting part of this evening, so I'll move on. So this mystery actually goes back almost a century at this point. Back in the 1920s and 30s, there were several observations that suggested that there might be something important we were missing in how the universe was constructed. And one of the clearest examples was this work by Fritz Zwicky from 1933, where what Zwicky was trying to do, he didn't realize that he was unveiling the first hints of a mystery that might transform particle physics. He was just trying to measure the mass of this galaxy cluster, which you see in this image on the right here. Now, if you want to try to measure the mass of a galaxy cluster, you can't exactly put it on your kitchen scales. It's a long way away and very heavy. So Zwicky is like, okay, I should do this 2 different ways and check that I get the right answer. We'll check that I get a consistent answer between both methods, and then that will give me a little bit of confidence that what I'm doing is sensible, since I don't have a lot of other ways to validate it. So his first method was basically to look at that image and say, right, how many galaxies can I see in this image? How much mass do I think each of these galaxies should have? I add them all up, I get a number, that tells me the mass of the cluster. Method 2 was a bit more indirect, was to say, okay, well, if I look at how fast these galaxies are moving, that tells me how much gravitational pull is being exerted on them by all the rest of the mass in the cluster. So I should be able to use that to tell how much total mass there is in the cluster. So and these both sound like very reasonable ways to proceed, but the problem is that the 2 methods give extremely different answers. The second one is larger by a factor of a couple of hundred. So that sort of suggests that there's a couple of 100 times as much mass in this galaxy exerting a gravitational pull as you can actually see in the visible galaxies. Okay, so that's a little puzzling. I mean, at the time, people thought, okay, maybe this just means that there's a great deal of mass in these galaxies that in between the galaxies, which is true, and that mass isn't shining for some reason. Doesn't necessarily tell us that it's some new kind of matter, but it's dark from this perspective. It's not showing up brightly. Now, the next big step forward in our understanding of what was going on with this missing mass came from observations at the galaxy scale. So this is the low-tech version of an observation of a galaxy. This is taken from a point on the coast of Australia, which is where I'm from originally. And this was a time-lapse observation. It's out in the darkness, so you can see the night sky very clearly. It's a time-lapse observation taken over many hours. And this band of bright stars across the sky is the Milky Way Galaxy that we inhabit. So if we could see this from the outside, it would probably look something like this spiral disk of stars with sort of bright spot towards the center. And I have marked with the blue dot roughly the position of the Earth relative to the galaxy as a whole. Since we're standing in the position of that blue dot, what we see when we look up at the sky is there's a particular direction on the sky that is where the disk of the galaxy lies, and that's this stripe of the Milky Way, which you can see very clearly from the southern hemisphere. Now, we can look at other galaxies as well with better telescopes. Some of them we can see side on, like this one, and we can observe how stars and gas clouds in the outskirts of these galaxies are moving. We can do the same kind of things as Zwicky did back in the 1930s and say, right, we can measure how fast these stars and gas clouds are moving. That tells us how strong is the gravity pulling on them from the inner parts of the galaxy. So in 1970s, a group of astronomers led by Vera Rubin, collaborators Ford and Thorned, they measured the rotation speed of galaxies using techniques like this. So what do you expect to see when you measure the rotation speed of objects in the outside of galaxies? If you look again at the visible matter, the gas and the stars, you see that most of it is sort of peaked in the center, which I've indicated by this yellow blob in the center here. And just using the laws of gravity that we learn in school, you can then you can predict how fast you expect these test particles to be moving around this central region. This is what you expect, and what you see is that close into the central region, they're going pretty fast. The gravitational pull is pretty strong, it's accelerating them, but out on the outskirts, these particles are moving extremely slowly. Right? This is what you expect from the laws of gravity as formulated by Newton, later amended by Einstein. You expect the velocity of the test particles to fall off away from the center. What you actually see, though, when you do this observation is something more like this. And if you compare these two, the particles towards the center are behaving similarly, but on the outskirts, you see that these particles are really going very quickly compared to what you would naively have expected. So this is sometimes called a flat rotation curve, which means that the particles out here are moving just as fast as the particles in there. The change in velocity the velocity level is basically flat between these 2 points. Okay, so what does that suggest? Well, it suggests that for whatever reason, gravity is stronger out here than you would have expected. In the inner regions, it's pretty similar, but in the outer regions, it's very different. So there are a couple of possible explanations for this. One is that there's extra matter out here, and you just can't see it. The gravity is stronger because there's more mass that gravitates. The gravitational pull of objects just depends on how heavy they are, so maybe there's more mass out here. But if that's the case, it's not just that this bulge, this blob in the middle is more massive than you thought it was. It tells you there has to be a lot of matter distributed in a way which really doesn't look like the matter that you can see. It's spread out much more broadly throughout the galaxy. So that suggests that the visible part of the galaxy that we can see is surrounded by this giant extended cloud of something that we can't see. And we call this a dark matter halo. So this is the dark side of the universe rearing its head for the first time. Does this laser pointer work? So that hypothesis would suggest that because the dark matter is distributed differently from the ordinary matter, it's not only different in being invisible, it also behaves differently to the ordinary matter in other important ways, i.e. that it hasn't collapsed down into this spiral galaxy. So one possibility that turns out to work pretty well is if you posit that this new form of matter really only interacts by gravity. So it exerts a gravitational pull, it experiences a gravitational pull, but it can't interact with light, it can't radiate photons, it can't bounce off other particles and transfer energy to them, then that would indeed give you a big fluffy cloud of dark matter surrounding the galaxy, which seems to agree reasonably well with observations. Now, of course, the other possibility is that your theory of how gravity works is wrong on these large scales. So how could we tell this apart? I mean, maybe gravity just doesn't weaken as quickly as you expect when you start looking at distances that are on the scale of the size of the galaxy. So how do you tell that apart from having extra matter, given that the extra matter is something that you can't actually look at with light? So the problem is that because the dark matter and luminous matter are gravitationally bound to each other, if that matter's there, you expect it to congregate in the same places as the luminous matter. So that makes it very hard to tell apart from the luminous matter just having stronger gravity. So a solution to this is to look at systems where galaxies or galaxy clusters are colliding with each other, where you have non-equilibrium systems and you can maybe break this connection between the dark matter and the ordinary matter. So the idea here is, okay, let's think about if I take clouds of ordinary matter and push them into each other, then what happens? Now we go back to our understanding of thermodynamics. If I push two clouds of gas into each other, they will exert a force on each other, they will compress each other, they'll exert a pressure, and they'll heat each other up. Now this is a system observed, so these pink regions here are showing regions that are glowing in X-ray. The reason that they're glowing in X-ray is because these two clouds of gas have just moved through each other, heating each other up and causing the heated gas to produce X-rays. This is called the bullet cluster because this shape on the right-hand side of the image looks very much like the distortion that you get from when you try to fire a bullet through a fluid. And it's a similar physics. But we just posited that that each of these galaxy clusters has a big halo of dark matter surrounding it, and that halo may not behave like ordinary matter, and in particular may not have significant interactions. So if something like that is going on, there's no reason that the clouds of dark matter should exert pressure on each other and heat each other up and slow each other down. So what you would expect, I don't know, can people see this? Is that, yeah, can we maybe switch the lights? Is it observable what the separation is? So here the blue, okay, yeah, okay, good, that's much better.
I can
Just momentarily, okay, so here the blue is indicating the dark matter clouds, the red is indicating a component that experiences collisions. So in this cartoon, as the halos run into each other, the blue regions just pass straight through each other, they don't collide, they don't interact, but the red regions are slowed down and left behind by their collisions. If something like this was going on, what you would expect to see then is that the gravitational effects of the blue regions would be separated in space from where all the hot gas is. And that's indeed what we see what the Chandra telescope saw when they did this observation in 2006. So this is the actual image. You can turn the light back on now, I think. Yeah. So that was actually what they saw when they made this image in 2006. The blue regions are where the gravitational effects of these clusters are strongest, as mapped out by how much they distort the light coming from behind them, how much their gravitational pull affects the trajectories of photons behind them. Well, there's the red regions where all the bright hot gas is, and you can see that there's a pretty distinct separation. So this is very hard to explain by just a simple modification to gravity, because even if you make gravity fall off more slowly at large distances, you would still expect that the gravity should be strongest where the mass is, not displaced off to the side from where the mass is. So this is one of the pieces of evidence in favor that what we're looking at is actually a new component of matter, as opposed to a change in how gravity behaves.
Sorry.
Yeah?
Can you please explain again how did they actually got this picture?
So the red images are X-rays. The blue images are a gravitational lensing map. So so I don't want to go into too much detail here because it's a little complicated, but basically gravity affects light as well. It bends the trajectories of light through space. So if you have stars in the background of this image, the light from those stars and galaxies as it comes to you will get bent by the concentration of mass in these regions. Using a computer program and a lot of background stars, you can reconstruct the mass distribution between you and the background stars, and that's how you make these maps of the blue emission of where most of the mass is concentrated. That's a good question. No, really good question. Okay, so then you might say, okay, so maybe you believe me that there's probably some new kind of matter out there. Are we looking at some kind of new particle, or are we looking at what the field likes to call machos, which are massive compact halo objects? The physicists like to cast this as the battle between machos and WIMPs, where the WIMPs were weakly interacting massive particles, and it may reveal some physicist prejudices that most of them seem to prefer the WIMPs to the machos. But yeah, so what's a macho? So a macho is what's called a massive compact halo object. So this is basically the question of, are we looking at a new particle, or are we looking at some like macroscopic objects that we could pick up and look at if we were close enough to them? So if I've got, say, a black hole that was formed in the very early universe, then that can act as dark matter from everything that I've told you so far. It wouldn't necessarily radiate light. If it's uncommon, they're pretty rare. You don't have a dark matter particle every few meters, so you don't have a black hole every few meters. So these black holes would be effectively non-interacting. They would really only interact through gravity. If you had a cloud of black holes and you passed it through another cloud of black holes, most of the black holes would never encounter each other, and so it would be effectively collisionless. So, and there are black holes out there, so the question is, could they be most of the dark matter? So there have been searches done specifically to look for this, and I guess I got a little bit technical here. So the strategy in the simplest of these searches is basically to say, all right, there's some distant star that I'm going to watch, or some collection of many distant stars that I'm going to watch. If a black hole passes between me and those different distant stars, then its gravity will act as a lens and bend light around it. And I'll see the stars briefly get brighter as the lens of the black hole magnifies them, and then get fainter again. So there have been long-running searches done with this strategy to try to look for tiny black holes. And in the first searches of this type, they would have expected 40 if the whole halo was made of black holes in their target mass range, which was around the mass of the sun. And they found one event that might have been something interesting. And they were able to exclude machos of masses between about 10 to the minus 7 times the mass of the sun. So this is about 1/10,000,000th of the mass of the sun, and 15 times the mass of the sun as the main constituents of our Milky Way's dark matter halo. There have been many other searches like this in the subsequent years. At this point, we can basically say that it's very hard for 100% of the dark matter to be made of black holes unless they're in this pretty narrow mass range, which is between about 10 to the minus 16 and 10 to the minus 11 solar masses. So for calibration, that's larger than the moon. It's about the mass of the larger asteroids in the asteroid belt. So you would need to have these tiny little black holes, and that, as I'll say in a moment, have been around for the last 13 billion years. But that's a possibility. So yeah, things you know of this general scale. So I just told you that we need these objects to have been around for most of the lifetime of the universe. This dark matter is a long-lasting feature of our cosmos. So how do we know that? Well, the reason that we know that is that we have observable signals coming from when the universe was only 300,000 years old, which was somewhere in the ballpark of 13 or 14 billion years ago. So, though that light gives us a picture of what the universe looked like when it was a factor of 1,000 smaller than it is today. This parameter z just says how much the universe has expanded since that time. So our universe has been continually expanding since the Big Bang. The last few billion years of evolution, we can probe back to 300,000 years from the Big Bang using the photons that I'm about to tell you about. So at that time, the universe was basically a soup of charged particles, of neutrinos, of light, and of, we think, the dark matter. At that time, before that time, the universe had always been almost completely ionized. There were no atoms, there were no molecules, there were certainly no planets or stars. Instead, the universe was just a plasma of ions, charged particles, and electrons. But around this time, at redshift 1000, the first hydrogen atoms started to form and formed rapidly, and the universe went from being almost completely charged to being almost completely ionized to being almost completely neutral. At that point, photons are very good at scattering off charged particles and rather bad at scattering off neutral particles, so that released a wave of photons which have been traveling towards us ever since. So when we see, this is called the cosmic microwave background radiation, the photons that we see in it, the last time they interacted with anything before they hit our telescopes was when the universe was only a few 100,000 years old. So we can take essentially a picture of what the universe looked like then, and this image, which is taken from the Planck telescope, is what it looks like. So this is a map of temperature. I think the red regions are hotter, the blue regions are colder. So you can see, it looks, for a map of the universe, this does not have very many dramatic features. So, as I said, the reason for that is that the universe was an almost perfectly homogeneous soup at that time, but there were regions, as you can see here, of slightly higher temperature and slightly lower temperature, and relatedly, there were regions of slightly higher density and slightly lower density. There were ripples in this bath, this primordial soup. So I'll say a little bit about how those ripples evolved in the future, but I can say we can summarize, so a map like this has a lot of information in it. We can summarize it by saying how much power there is in this map on different angular scales. So how many fluctuations there are that are small scale versus how many fluctuations are that are larger scale. And that's a convenient way to summarize this picture. So what's the physics going into this picture? The physics, so suppose in the early universe, suppose I have some region that just by coincidence is a little bit more dense than the region surrounding it. Then what will the effects of gravity be? Well, under gravity, the dense region will attract other regions to it, so that pushes the density upwards. But if I'm trying to cram together a bunch of charged particles, then the pressure of radiation, or electromagnetic repulsion, will push them back apart. This leads to oscillating ripples in the data where the density rises for a little bit, then the radiation pressure pushes those particles back apart and the density goes down. So, but the nature of these fluctuations depends pretty sensitively on this balance between the effects of gravity and the effects of radiation pressure. If we have a component, which we call dark matter for these purposes, that doesn't feel the radiation pressure and that only feels gravity, then its effect on these ripples is quite different to visible matter, which feels both. So if we model the universe as a bath of photons plus ordinary matter, which I'm calling baryonic matter here, which feels both gravity and radiation pressure, plus a dark matter component, which doesn't feel this radiation pressure, and I ask, let's look at that summary picture on the previous slide that tells you how much power there is at different scales, then what I'm going to show you here is what happens as I change the amount of dark matter in my model. So at first, with no dark matter in my model, I would predict that this plot of how much power at different scales should look like this. There's a big peak at this intermediate scale, and then it drops off. As I change the amount of dark matter, the nature of these oscillations changes, and this pattern changes pretty dramatically. It turns out that there is an exactly one value of the amount of dark matter that gives an oscillation pattern that matches what's actually observed in the data. And that corresponds to a dark matter component that has about 5 times more mass than the baryonic matter. So it's a hypothesis that what we see in galaxies and in galaxy clusters, the missing mass there is the same as this dark component that only feels gravity and not radiation pressure in the cosmic microwave background. But so far the evidence seems to be pointing in that direction, that what we're looking at is one extra component for our cosmos that has been around at least since the first few hundred thousand years of our universe and surrounds every galaxy and every galaxy cluster in the present day. So these little oscillations, these ripples, when the universe was only a few 100,000 years old, we believe that they later grow into giant structures. So there are a few possibilities here. If the dark matter was very fast moving, well, these ripples would exist at early times. They would not grow rapidly, at least on small scales. So in this picture, I have regions of the universe that are a little bit denser than others. They're starting to grow under the effects of gravity, but if the dark matter particles were flying past each other at the speed of light, they just wouldn't end up sticking to these regions of high density. On the other hand, if the dark matter is slow moving, what happens is that each of these high density regions becomes a clump of dark matter, which continues to grow under gravity. Over time, those clumps accrete together, like producing snowballs, to grow into larger clumps, larger halos, and filamentary streams of dark matter. This plot on the right is a simulation of what the invisible dark part of the universe would look like if we could see it today. So this web-like structure, we think, is underlying everything that we actually see. In the regions of high dark matter density, then the gravity of the dark matter pulls the visible matter onto it. So the reason that galaxies are surrounded by clouds of dark matter is that the cloud of dark matter formed first and then the galaxy formed within it. So it's in that sense that we believe that this dark matter forms the scaffolding for the visible universe that we can see today. Okay, so that's more or less our evidence for that. There's a component called dark matter. It's been around for essentially the whole age of the universe. It underpins all the structures that we see in our cosmos in the present day. And we don't understand what it is, because in order to explain this, we need something that's stable on cosmological timescales. It doesn't decay away. It doesn't collide effectively with other particles based on the bullet cluster and its cosmology. And it can't be moving too fast when these giant structures are being formed in our universe. So the only particles that we know of that satisfy the first two are the neutrinos. So the lowest mass of particles in the standard model. And the neutrinos, they're too light. They're moving too fast. They would behave like hot dark matter. They would fly past each other and not form the scaffolding for the galaxies. So if we want to do this with a particle, we need at least one new one. So it's one of the most powerful pieces of evidence we have that there is some physics out there that we don't understand, that there are some new particles beyond those that we usually think about. But everything we've learned so far has come mostly in the form of negative results and has come from studying just the gravitational effects of dark matter. So let's get on to the next bit about how might we go beyond this? How might we look beyond the gravitational effects of dark matter? So when I looked up the scientific method on Wikipedia, I got a diagram that looked something like this. And dark matter, occasionally, the dark matter hypothesis is accused of being unscientific, but this has really followed a very straightforward trajectory. We observed the first hints of dark matter. We saw that clusters didn't have the masses that we were expecting them to. We saw that particles didn't move around galaxies the way that we expected them to. We could ask, okay, the question of what's causing that, and one pretty simple hypothesis is that just there's some extra kind of matter in the universe that we can't observe. if you say that, and if you hypothesize, okay, let's suppose that the reason it's behaving differently is because it doesn't have the same interactions, then you might say, okay, well, we can look at colliding galaxy clusters to try to filter the dark matter from the standard matter, and we can look at the effects on cosmology. We can look at the effects of the early universe. And so far the observations seem to largely validate this general picture, although there are some observations at small scales that we still don't totally understand. So this leads us to, okay, we have this general picture of what's going on, that we have this standard cosmological model which has a dark matter component in it. Great, okay, but let's move on to the next question, which is, okay, so we have a hypothesis, we have there's something that we call dark matter, which experiences gravitation, it doesn't experience radiation pressure. So next, let's try to answer this next question, what is it? So here we're at the stage of, okay, we've made some observations. There appears to be a component that we can call dark matter that is present in the universe. So think of interesting questions. Well, yes, that's pretty easy. We talked about this already. There are lots of possible things that you could ask about this stuff. Then we get to the formulate hypotheses stage. Well, and I'm a particle theorist, so at this point, what happens is something like this. So our problem is not that we don't have ideas for what dark matter could be. We have an enormous number of ideas for what dark matter could be. This is taken from a talk by one of my colleagues as part of a process that the US particle physics community went through about 5 years ago. And I definitely don't want you to read and understand everything on this slide, so I'll just say a couple of things. Everything within the red line on this slide is a general class of scenarios for dark matter. It's not even like a specific theory for dark matter, it's a class of possibilities. Everything outside the red lines is some broader theory of new physics to which dark matter could be connected. So I want you to take away about 3 things from this slide. Thing 1 is there are lots of ideas. Like we don't have any problem with not having ideas for what dark matter could be, although of course it's still an open question as to any of them are right. Point number 2 is that if we could figure out what dark matter was, it could potentially unlock other mysteries of physics beyond the question of just what is the 80% of mass that we don't understand yet. Dark matter could be related to some fundamental new symmetries of the universe, some new laws of physics in the context of supersymmetry. It could reveal dimensions of our universe beyond the 3 space dimensions and 1 time dimension that we usually think about. It could be related to the Higgs boson that scientists at the Large Hadron Collider found about 7 years ago in 2012. It could be related to the physics of the strong nuclear force of the Standard Model, and there are still deep unsolved mysteries there. It could be related to neutrinos in some way or another. It could provide a gateway to new forces that are experienced only by the dark matter and not by the visible matter. So it could be a key. And the third point that I want you to take away is that so far every single idea on this slide is not excluded by experimental data and is consistent with the observations, because everything on this slide has the dark matter has gravitational interactions, it has mass, and it doesn't have interactions that are strong enough that they would already have been seen. Like everything I've told you so far, all of these possibilities are essentially indistinguishable.
Sorry?
Yeah?
Black holes were not included.
Good. Yeah, so this is even like theories of particle dark matter. So primordial black holes sort of get to live off in their own little area because they're very different from everything else. But yeah, it's definitely worth keeping in mind as a possibility. That also applies to this, incidentally, that if there really is a big bunch of primordial black holes at asteroid masses, that would tell us a lot about inflation, the beginning of the universe, because you have to seed them somehow when the universe is less than a few 100,000 years old. So that would be a pretty unique insight into what was going on in the earliest instance of the universe. It would be a key to unlock other physics. And from a gravitational perspective, there's not a lot of meaningful difference between an asteroid-sized primordial black hole and many fundamental new particles. But yeah, it's worth keeping that in mind.
Hasn't anything changed until the 1930s?
Yeah, well, so I could certainly add more things to this plot. Yes. I mean, some constraints have gotten better, but I don't think much has changed in the context of completely, I mean, these are large categories of models. So within any of these categories of models, some regions will have been ruled out, But in terms of just completely killing whole scenarios of models, no, I don't think we've made a ton of progress since 2013. I mean, some people are significantly more skeptical about supersymmetry than they were before, and that's reasonable. But I mean, there are still models of supersymmetry where the bottom of the SUSY spectrum is a dark matter candidate at 1 or 3 TeV, and that's not really testable by the LHC. Is there a question there?
Does the dark matter exist since the Big Bang?
So it needs, yeah, so we don't know. Like, so the first like really clear handle, the first time that we really have an opportunity to measure how much dark matter there is in the universe is the CMB, which was emitted at redshift 1000 when the universe was a few 100,000 years old. Depending on your model, the dark matter could have gotten its present abundance at a wide range of times in the early universe. Yeah, I mean, like there are models where it wouldn't get its correct abundance until the temperature of the universe was about a keV, so that's after Big Bang nucleosynthesis. It's well after baryogenesis. There are other scenarios where it's been around, and there are other scenarios, well, in the QCD axion case, it mostly gets its abundance at the QCD phase transition. There are other cases where its abundance could have been set extremely early in the universe. So before this, it has to have been around since the universe was 300,000 years old, but before that, we don't really know. So if we want to try to distinguish these models or determine that none of these are really viable, the way that we can tell them apart is that they predict really different interactions between dark matter and ordinary particles, or sometimes between other dark matter particles. So if we could detect any interaction between dark matter and ordinary particles, it would instantly allow us to rule out most or all of what I wrote on the previous slide. So that's kind of the goal of a lot of work in this field, is to try to find some non-gravitational interaction between the dark matter and the visible matter. So what kinds of interactions might we look for? There's a wide range. The one that I'm going to talk about in the rest of my time is the possibility of looking for dark matter annihilation signals. This is not a guaranteed signal. I hope I convinced you from the slide a couple of steps back that except for gravitational interactions, there are not any guaranteed signals. These models have very different signatures. For any given signature, you can find a model where that signature just doesn't exist. Okay? So this is a thing to look for, but there's not a guarantee that we will find it. So that said, this is a pretty common and ubiquitous possibility that occurs in a lot of dark matter models, that it could be true that when two dark matter particles run into each other, they could produce visible particles, the same way that we can smash visible particles together at colliders in order to look for new particles. And we can look for dark matter in that process as well. So the picture here is that two dark matter particles come in, a miracle occurs. This is the new physics that we would like to probe. Standard model particles are produced. This could be quarks, they could be leptons, so like electrons and positrons, they could be the gauge bosons, the W and Z and Higgs bosons of the standard model. Once they're produced, most standard model particles are unstable, so they'll decay, producing the long-lived known particles: photons, electrons, positrons, neutrinos, protons, and antiprotons, and occasionally heavier nuclei. So these are the objects that we want to look for in these searches. So what can you do with dark matter annihilation? Well, first, this kind of annihilation process could actually explain why we see the abundance of the dark matter that we do today. I told you that it's about 5 times as much mass in the universe as the ordinary matter. There are classes of scenarios where this is just completely controlled by how well dark matter annihilates. If it annihilates too well, there's very little dark matter left today. If it annihilates too slowly, there's too much dark matter left over. So if you want the Goldilocks regime of just the right amount of dark matter, that actually tells you how fast this annihilation rate is. If something like that was happening, there was a steady annihilation rate of dark matter, then throughout the whole history of our universe, the dark matter particles would have been steadily converting the energy stored in their mass into heat and high energy particles. And those effects could have reshaped our universe in measurable ways. But that's a different talk, which I can tell you more about that later if you're interested. But what I want to talk about for the rest of my time is the possibility that we could directly observe the standard model particles that are produced in these dark matter collisions. We could look at regions where the dark matter density is high and see standard model particles appearing apparently from nowhere. So if that's what you want to target, then so you should broadly look at photons across a whole range of energies. You should look for charged particles. You should look for neutrinos. But in particular, If the dark matter is up in the kind of mass range that the Large Hadron Collider is trying to probe, or somewhat heavier, then the dark matter, or say it another way, if the dark matter is as heavy as the heavy particles we know about, like the Higgs boson and the top quark and the other gauge bosons, then when they collide, their mass energy could be converted into very high energy photons. So gamma rays are the most energetic form of radiation. This is just a sketch of the electromagnetic spectrum. The light that we see by is in this optical range. It has typical energies of about an electron volt. The gamma rays that I'm talking about, the lowest energy gamma rays I'll be talking about have about 1 billion times more energy than the light coming from the lamps in this room. So, okay, this sounds good. Very, very high energy particles. They occur only in violent events. You don't see them every day. But there are some processes out there in our galaxy which are energetic enough to produce these very high energy particles. In particular, they dominantly come from very high energy cosmic rays running into the gas that's out between the stars in our galaxy. So this is a cartoon that NASA made of that process. If you have a very high energy charged proton streaming through our galaxy, then it can interact with the existing gas and make an unstable particle called a pion. That pion later decays into gamma rays, into high energy photons. So our galaxy is a sea of charged particles, so collisions like this are happening all the time and produce a lot of photons. But because they require the cosmic ray to strike the interstellar gas, the map of photons from processes like this looks very similar to the map of interstellar gas in our galaxy. That map looks like this. So this is an image of the sky that's been stretched out onto a rectangular grid. The center of the Milky Way Galaxy is in the center of this image. This bright bar along the center is the disk of the Milky Way, just like the image of stars that I showed you earlier on. So, and you can see that most of the gas in the Milky Way is concentrated along this disk, but there's quite a lot of streamers and clouds of gas extending above and below the galactic plane. So if we want to look for a dark matter signal in gamma rays, we're going to be looking for it on top of this background. So, but okay, we can do that. So we can build a model for what we expect the gamma rays to look like from these sources, from these charged particles interacting with the gas in the starlight. It looks something like this. So this looks pretty similar to the gas map that I showed you earlier. So in 2008, NASA and DOE launched a new gamma ray space telescope. This is a picture of the launch. It went up from Cape Canaveral in June 2008 and has been in low Earth orbit ever since. All the data is fully public. Any of you can download it from the internet. That's what me and my group did. We're not members of the experimental collaboration. The telescope that was put on this rocket is now a satellite. It scans the entire sky every 2 orbits around the Earth. It orbits about once every hour and a half. And it can measure gamma rays from 300 MeV up to several TeV. So this is 0.3 GeV up to several thousand GeV, and a GeV is 1 billion times the light from those lamps. So what do we see? So using this telescope, we were able to make a map of all the gamma rays in the sky. This was made back in 2010, so it's a bit cleaner now. Just want to show you what it looked like soon after we got the original data. So this is a map of all the gamma rays in the sky, except that we have subtracted off some very bright individual sources of gamma rays, and we've cut out some regions where that subtraction was done. And you know, at first glance, this looks broadly speaking like that gas map I just showed you. There's this big, so black here means more gamma rays. There's this region of intense gamma ray emission along the disk of the galaxy, and then there are these gas spurs and clouds above and below. But there's actually some stuff in this image that was not there in the model, and which indicates an excess over this background emission. But first, I'm just going to ask, does this plot make sense to people? Do you understand what you're looking at? Because if not, now is a good time to ask questions. Okay, so we can take this data and just subtract off the model map that I just showed you. So we're just saying this is what we actually see minus our expectations. If we do that, we're left with something that looks like this. And you may see now that there's a structure here, kind of figure-8 shaped structure, which represents a difference between our expectations and what we actually saw. So these structures are what we called the Fermi bubbles. They were first described in a paper where I was one of the co-authors back when I was a PhD student at Harvard in 2010. And these were a completely unexpected feature of our galaxy in high energy gamma rays. This is a slightly better picture that makes it a little easier to see the bubbles. They're this orange and white region. So these structures are enormous. They're about 50,000 light years from top to bottom. They bright in gamma rays between about 1 and 100 GeV, and we also now see them in photons of other energies at X-ray and microwave levels. They may be telling us about what the black hole, so there's a giant black hole in the center of our galaxy. These bubbles may be a relic of activity that occurred at the black hole over the last several million years. But they have a lot of puzzling features, and their origin is still an open question. One point that's very obvious is that these are not coming from dark matter or anything related to dark matter. I told you on these gamma ray searches is a way to look for dark matter, but the halo of the dark matter around the galaxy is a cloud shape. There's no reason for it to look like this figure 8 shaped structure. But okay, so that's interesting. But it's not what we were first looking for. So if we wanted to look for a dark matter signal, what would that look like? So we can do two things when we look for a dark matter signal in photons. We can look for how the number of photons changes as a function of energy, so how many low energy photons you have versus mid energy photons versus high energy photons. And we can look at how it's distributed on the sky. So we said earlier that our galaxy is surrounded by this big puffy dark matter halo. So whereas the bright emission is in this band across the sky, a dark matter signal should look more spherical, more like a soccer ball. A football notation here. So there's an American versus European convention here, but so it should look more spherical rather than following a band across the sky. The other thing so on the energy information, this is an example of if the dark matter particles collided with each other, made standard model particles, and then those standard model particles decay. These lines are showing how much power you would expect as a function of energy in photons of different energies. These are, again, units of GeV, about 1 billion times the energy of the light from the lights. And these correspond to different models of dark matter, different things it could annihilate into, but you can see that in every case there's kind of a bump. There are more photons at a specific energy and fewer photons at both higher and lower energies. And that's a pretty generic signal of dark matter because the dark matter has a specific mass scale, and that's what determines the preferred energy of the photons that come out when they collide. So if we want to do a dark matter search, where should we do it? Well, the center of our galaxy is the center of the gravitational potential. It's where the effects of gravity are strongest. And if the dark matter is only interacting under gravity, you expect the density of the dark matter to be highest here. Now, the downside, of course, is, as we just saw, there's a lot going on along the plane of the galaxy. There's a lot of bright gamma ray emission from gas. And so this is a pretty complicated region, but it's also where we expect our signal to be largest. If we're going to disentangling it from the backgrounds may be hard, but if we're going to see something, this may give us our best chance of it being discernible. So immediately after the Fermi data became public, so the spacecraft was launched in 2008, the data became public in 2009. About a month later, two scientists at Fermilab in the US, Lisa Goodenough and Dan Hooper, pointed out that there was something funny going on at the galactic center, something that we didn't expect. So this is a zoom in of the region around the galactic center. This plot on the left is the emission that was seen before you tried to subtract off your model for the expectations. This is just what people saw. And then, so this is from a later paper, this is not the original from a few years later, it just has a nicer picture. Once you do the exercise that we did before and subtract off your model for the expected signal, what's left is this blob. Now, I should say that the color scale on these two plots is different by a factor of 3. This blob is about 1/3 of the bright central part of this excess. But that blob is kind of interesting because it doesn't look at all like the disk of the Milky Way. It doesn't look like a band. It looks like something more spherical. But at first you might say, yeah, but okay, this is a zoom in. Like I said, the scale on this plot is that this blob has about a 1-degree radius. We know that the Milky Way has a big black hole at the center of the galaxy. Maybe this is light associated with the matter falling onto the black hole, something like that. But as we did follow-up studies, and one of them led by my colleague Tansu Dylan up there, we found that actually this blob, you can't see it on this plot, but it extends much further out, and it fills the whole region within about 5,000 light years of the galactic center, which tells you that it's not just something associated with the black hole at the very center. If we ask what is the energy spectrum of this excess, so we ask how much power there is at different energies, that's captured by these red and black points on this plot, and this blue line passing through them is an attempt to describe those points with a simple dark matter model. And you can see it can go through the points pretty well. So after many years of study of this excess, basically where we stand is this blob appears to be really here. It doesn't just appear to be a mistake in the simple background models we tried. It's brightest at energies between about 1 and 3 gigaelectron volts. It's steeply peaked towards the center of the galaxy, but it fills the whole region within about 5,000 light years of the galactic center. And at least the central part is pretty spherical. The outskirts, it's not so clear, but the central part still looks pretty much like this. Furthermore, if you ask, okay, suppose this was a dark matter collision signal. Suppose it was those dark matter particles in the cloud around the galactic center colliding together and producing gamma rays, you can figure out what kind of annihilation rate you would need to get this signal. And it's basically exactly what you would need to get the right amount of dark matter in the present day. So if the annihilation rate was much larger than this, you would not have enough dark matter left. If it was much lower, you would have too much dark matter left. So that's either telling us something important about dark matter, or it's an interesting coincidence. It may be an interesting coincidence. So what are our hypotheses for these? Well, there's the one that gets particle theorists all excited, which is we've just discovered, or well, 10 years ago, we discovered the first signals of dark matter interactions with the standard model. And this, maybe it is a dark matter annihilation signal. But of course, anytime you see something like this, especially at the galactic center, you have to think about the possibility of it being what particle theorists call conventional astrophysics, i.e. physics that doesn't actually require adding new particles to the standard model. So the two sort of leading explanations that people think about here, one is we know that there are some stars that emit gamma rays. Stars emit light. The stars like our sun don't emit a lot of light at this high energy, but there are stars that do. In particular, very rapidly rotating neutron stars can spit out photons at equally high energies to what we're seeing in this excess. The other possibility, well, I told you that you get cosmic rays, that you get these high energy photons by charged particles flying through the galaxy, interacting with the gas in the starlight, and producing high energy gamma rays. So maybe there's an extra source of high energy cosmic rays, a burst of these things flying outwards from the galactic center. From a particle theorist perspective, these are sad options, but from an astrophysicist perspective, these would both tell us something really interesting about what's going on in the heart of our galaxy. So what about outbursts? So this is actually my least favorite explanation, so I'll just mention it briefly. So the idea here is, well, the black hole at the center of our galaxy can emit jets. You can also have explosions of giant stars going off in supernovae. That could produce high energy particles streaming out of the galactic center. Now, when they interact with the gas or the starlight, they would produce gamma rays, and we know that such events have definitely happened in the past because you almost certainly need something like this to create those giant bubble structures that I told you about earlier. So, okay, so this sounds pretty good. The disadvantages are that, well, I told you earlier, these charged particles interacting with the gas, they make a signal that looks like the gas. And the gas looks mostly like that band of the Milky Way. Our signal doesn't really look like that. The signal doesn't seem to be brighter where there's a lot of gas, and if the signal, there's another possibility, which is that the signal comes mostly from electrons scattering on high energy light, but it's pretty hard to match both the energy and the spatial behavior of the excess in that case. So this is a possibility, but I think it's probably not all of what's going on. So the next possibility, which is my favorite astrophysical explanation, which is that what we're looking at is a population of spinning neutron stars called pulsars. So these are pretty extreme systems in themselves. These stars are composed of ultra-dense neutrons, so just neutrons packed down tightly, no protons. When they spit, they can whip around at 1,000 times a second. These millisecond pulsars they can produce radiation at all sorts of wavelengths, but in particular they can produce these high energy gamma rays. And the Fermi telescope has observed some of them and sees that indeed they have spectra that peak at 1 to 3 GeV, just like the excess. the way that we think you get these millisecond pulsars, they were once younger pulsars, they spun down, but they're often in binary systems with other stars, and when those stars swell up and become red giants, the pulsar can start eating them, essentially, can start cannibalizing them, and using that material to spin itself back up so that they end up going around extremely quickly. So the hypothesis here would be that we have thousands, maybe tens of thousands of these millisecond pulsars living in the region around the center of our Milky Way galaxy, each one contributing just a few photons to the excess that we see. Because we've looked for bright spots of emission in the center of the galaxy, and we don't see any that are especially bright. So the advantages of this are, well, we know that these things can emit gamma rays at the right energy. That's really good, because we don't actually know that dark matter can emit gamma rays at this energy. We have many models where it could do that, but we don't know if they're real. Whereas pulsars, we've observed it, they definitely do emit gamma rays in the right band. There have also been some recent studies that say that while the central part of the excess is very spherical, maybe the outskirts of it look less like the dark matter cloud around our galaxy and more like the distribution of stars that we observe in this region. Now, this is a pretty hard analysis to do because you're looking really at the outskirts of the excess. The excess is pretty faint there. The uncertainties are pretty large, but this is maybe another piece of evidence in favor of it being pulsars. But we've never found a single millisecond pulsar in this region of the sky. We don't know of any millisecond pulsars in the galactic bulge. So if it's true, this may be the first hint of a whole new pulsar population. So that would not be quite as exciting as dark matter, but would still be pretty good. So where do we go from here with this story? Well, we could, and people did, spend a lot of time just asking the question of, well, which is more implausible, that we have a whole new pulsar population or that we have dark matter at this 50 to 60 GeV mass range? There's a range of things that you can do, but I want to tell you about one, in my last few minutes, I want to tell you about one strategy for trying to tell them apart. So one thing that you can do is try to distinguish between these two options by looking at how clumpy the photons are. So you can imagine these two scenarios where if this signal is mostly made of of collisions between dark matter particles in this smooth cloud of dark matter around our galaxy, you would see essentially this smooth blob of signal. But if what you're looking at instead is 1,000 individual stars, each of which are emitting in gamma rays, then you would see these bright hotspots, and also regions where there's just no emission because there are no stars in that there are no pulsars in that particular direction. Now, it seems like at first, okay, this should be really easy. It's very easy to look at these two images and say, well, this one is not the same as this one, so can't I look at the real data and just tell you which one it is? The difficulty is that looking at gamma rays with the photons is like, it's like looking at a picture with by somebody who has very bad vision, because when Fermi sees a star, it actually spreads out all the photons from that star over a region in the sky that is about the size of the moon or the sun. So if you imagine looking at the sky and every star that you see was spread out to the size of the moon, that's what the sky looks like from a gamma ray telescope. At least from this gamma ray telescope. So we have to take that into account, and also we need to take into account that these signals are sitting on top of all that gas correlated emission that I told you about. So nonetheless, back in 2015, we built a method to try to do this analysis, and what we found was that, and I'll say more about this in my lectures tomorrow for the people who are going to be here for that. But broadly speaking, what we found was we ran an analysis to try to distinguish between these two possibilities, and we found that the analysis really, really preferred having a bunch of individual point sources. So not a smooth signal, so not dark matter, pulsars, case closed, or almost closed. I'll tell you the loophole in a moment. What this plot is showing is the probability that a certain fraction of the total photons in the region come from various different components. The different colors correspond to different components. This first box is showing what happens when you only allow there to be a dark matter signal, you don't allow there to be a pulsar signal. The red line shows the result for the dark matter. You can see that it's peaked at a value on the x-axis of about 7 or 8%. That's about the total amount of photons that are due to the excess in the region that we're looking at. So in this case, your dark matter signal is picking up the whole excess. This larger plot shows what happens when you also allow there to be a pulsar population, which is the orange line, and the red line is still the dark matter case. So in this case, what happens is the analysis is like, oh yeah, 7 to 8% of the total photons in this region are definitely from pulsars, and none are from dark matter to a good approximation. So that, yeah, so that's the bottom line of that analysis. So if this is real, then by doing this search for dark matter in the inner galaxy, we've discovered this new pulsar population. And the question still remains, well, where did these objects come from? One possibility is that this is really giving us a handle on what the history of our Milky Way galaxy has looked like over the last several billion years. Because one way you could get these pulsars is there are little clusters of stars called globular clusters orbiting around the Milky Way, and we know that they have millisecond pulsars in them. It's possible that when those clusters came in too close to the galactic center, they could tear apart and spill out their pulsars into the region around the center. If that was happening, then these pulsars, this gamma ray signal, might be the last relic of star clusters that existed billions of years ago. So we'd really be doing galactic archaeology. This is a plot showing this scenario. The data points are showing the measured distribution of the excess as you move in towards the galactic center. So this side of the plot is towards the galactic center, this is further away, and the blue line is this model that's based on globular cluster disruption. So if these are pulsars, we don't know exactly where they came from, but they may give us a pretty powerful new handle on the history of our galaxy. So I'll give you one last thing. There is still some possibility that this excess that we're looking at is dark matter annihilation. I would not bet your house on it, or things much smaller than your house on it. But it turns out that argument that I just gave you, that based on this statistical analysis, it's all pulsars, may not be quite airtight. So the statistical method that we developed relied on having a pretty good understanding of what's happening in this complicated background. If that model's not good enough, you could have a situation where what's really going on is this, but because you mess up the background model, it looks a lot more patchy and a lot more scattered, and you misidentify it as point sources. So we actually were able to show, so my postdoc Rebecca Lean and I were able to show that at least in the analysis that we did in 2015, there's some evidence that something like this might be happening. So the zeroth order test for this is you say, okay, so I've developed this pipeline, and when I run it on real data, it says this signal is 100% point sources and definitely not dark matter. So you can validate this by saying, well, okay, suppose I take my real data and then I simulate a dark matter signal, and I add that dark matter signal to the real data. Now, if I run the same pipeline on it, I should get back that now some of my signal is dark matter, the stuff that I put in, and some is point sources. Okay? So this is the test that we tried. And unfortunately, that test is not passed. When we do this, it turns out that the analysis thinks that the injected dark matter signal is also 100% point sources. And you can add more dark matter, and you can keep adding more dark matter. And it turns out you can add about 5 times as much dark matter as would actually be there in the whole excess if it was coming from dark matter. And the fit is just like, yep, totally 100% point sources, definitely pulsars, no dark matter to see here. So this does not tell you that the real answer is dark matter. It just tells you that there could be a dark matter signal hiding in this data set, and some of the methods which were previously used to make at least one of the methods which was previously used to make pretty strong claims about it being pulsars may be getting confused by the background modeling. So it's maybe not quite dead just yet. Okay, so the basic problem, I hope I've persuaded you that there's a basic question to answer here, which is dark matter is more than 80% of the matter in the universe, and we don't know what it is, although we have a non-negligible amount of information about its properties. One way to try to get at what the dark matter actually is and try to search for its non-gravitational signatures is to look for particles produced by dark matter annihilation and what they could do to our universe, both in the early universe and in the present day. We probably haven't found it so far. there is a slight chance that we have found it and we just don't know what we're looking at. But we've developed these in developing these sensitive searches to go after dark matter, we have found that the black hole at our galactic center or the region around it was apparently blowing giant gamma ray bubbles. And we may have found the first evidence of an unexpected new population of pulsars in the very heart of our galaxy. The search for dark matter continues. There are many other ways to search for it that I haven't told you about tonight. There's new data coming in, both from the sky and from Earth-based experiments all the time. So stay tuned. And thank you very much for listening. Questions? Yeah.
So if the millisecond pulsar scenario is correct, can you explain Fermi bubbles?
No, the Fermi bubbles probably have to be something else. So, I mean, it's a fair question. To be fair, we have not we have in recent unpublished work checked if the Fermi bubbles appear to have evidence for point source C structure, the way that the galactic center excess does, and we don't find any evidence for that. The Fermi bubbles seem to want to be pretty smooth. This is also what you'd expect because the Fermi bubbles, you can only see it a little bit in those plots that I showed, but if you try to do an analysis of how sharply they fall off at the edge, it's really pretty sharp. Like the morphology. So, okay, closer to the galactic center, it's hard to tell what's going on. So I'll cut out this region, but if you look at the high latitude region and you look at how the emission falls off from like the center of the Fermi bubbles to the outside of the Fermi bubbles, if I were to plot the brightness as a function of distance along this line, it looks basically like this. I mean, it looks very stable, and then there's a step function, and then it's much lower. So it would be a little surprising if that kind of sharp edge structure could come about just through some distribution of point sources. It would be strange to have them confined, because again, point sources, the pulsars would be stars, right? So they're essentially collisionless. They're probably sort of somewhat like dark matter in that sense, in that they, it would be hard to say confine them with magnetic fields because they don't carry charge. So these edges are probably telling you that there's like some shock front propagating outwards at the edges of the bubbles. And this point we're looking at is like either where the shock front has gotten to, or it's kind of where it stalled out as it was trying to expand into the medium around the inner galaxy. So it's probably reflecting some kind of transient structure. The other possibility is that there's like a magnetic field draping this region and keeping charged particles and confining the charged particles inside. The scary thing about that is that, I mean, as I said, these structures are like 30,000 light years tall. So I mean, if there's some kind of coherent magnetic field structure that's draping these, then it's very, very large scale. So yeah, so no, the Fermi bubbles are probably, yeah, so the only explanation that would try to get both the Fermi bubbles and the galactic center excess together is something to do with cosmic ray emission, I think, because I think you basically need that to get the bubbles right. And you can, it seems very hard to do that to get all the properties of the galactic center excess right, but maybe there's a way. Or maybe there's just a coincidence.
Thanks for the talk. I was wondering, could it be possible to identify point sources better if you have a high resolution X-ray telescope in the sky?
Good.
What prevents it?
Yeah. So if we had a higher angular, right? So good. So this gets at two questions. So right. So this gets at two questions. So first, do these point sources emit in X-rays as well as radio? If they're pulsars, the answer is probably yes. We know that these gamma ray pulsars often do also have X-ray and radio counterparts. At the moment with the currently planned experiment, so it is angular resolution that you want, not energy resolution. You want to be able to localize these accurately. So probably the thing that would be convincing in both radio and X-ray is not just to find the sources, but to find pulsations if you wanted to make the case that it was a pulsar radiating gammas. It's like, especially in radio, the problem is we have radio telescopes with excellent angular resolution, but the gamma ray angular resolution is just not very good. I mean, like I said, it's about the size of the moon on the sky. It's like half a degree. So if I ask, I see some hotspot in the gamma rays where I think there might be a pulsar. Is there a radio source aligned with that gamma ray source? The answer is always yes. But it's true that like for every half-degree radius spot on the sky, there are a ton of radio sources. And that's not quite as true for X-ray sources, but I think like it's still broadly true. In this region around the galactic center, there are often multiple X-ray sources that are within the 0.5 degree region where you think the source is from Fermi. So making the X-ray resolution better on its own will not really help with that. But if you were to use the improved X-ray resolution and or sensitivity to be able to isolate the source and say, right, there's a source here and it has other properties which make me think it's emitting in gamma rays. So like a spectrum that's characteristic of pulsars or pulsations that are characteristic of pulsars, then that could potentially be a pretty compelling handle on figuring out what's going on. I mean, I think honestly the best way to fully confirm the pulsar interpretation, the shortest term way that I see to fully confirm the pulsar interpretation of the XS is to see the radio pulsars in the Meerkat telescope, because Meerkat's already built and taking data. And there was a study a few years ago that found that if the excess was 100% from pulsars, then Meerkat should be able to see several tens of pulsars. And several tens is enough that you could try to get the spatial distribution. Because like just seeing one pulsar doesn't really tell you anything, because it could just be along the line of sight to the galactic center. But if you can get a significant number, then you can start doing morphological studies. And if you find something that looks like the XS in terms of spatial distribution and are pulsars, then I think you're done. I don't think there would be any reason to look for another explanation at that point. But yeah, so I mean, depending on the, but yeah, so I mean, X-ray, X-ray similarly, it would depend on the ratio of X-ray to gamma rays, because we're not really in a soft gamma ray band here. But yeah, potentially, I mean, also if the X-rays could find sources which have the right properties to be gamma ray emitters, that could also be pretty powerful. But doing the direct comparison, the weak link is the gamma rays.
Are there new telescopes planned in the near future?
Yeah, so the Meerkat telescope that I mentioned, I mean, that's not new, it's been built, but it's not obvious how long it will take them to do this kind of survey of the galactic center region. But and then the SKA, which is the next gen radio telescope, is meant to be able to find hundreds of pulsars in this population if they're actually pulsars. So that would, yeah, I mean, if you find hundreds, that's fantastic. Then you could maybe actually start testing these hypotheses for the origin and trying to understand where they came from. Yeah, in the X-ray. Yeah, I mean, in the X-ray band, we talked a bit to people in NuSTAR because it's already at the level that if you just ask, given this total normalization of signal in gamma rays, how much X-ray flux would you expect to be showing up on NuSTAR? If you got lucky and the pulsars were all relatively loud in X-rays compared to gamma rays, it's already kind of the borderline of what they could see. So yeah, I don't know if future X-ray telescopes will be sufficiently better than the existing ones to be able to be able to get to the point where you don't have to be optimistic and you could be pessimistic and still see a signal. Yeah, so yeah, maybe.
I guess from the number of periodicities, you can have an estimation on the number of pulsars around there. So does it match with the gamma ray signal?
Sorry, what do you mean by the number of periodicities?
For example, there is a periodicity in frequency 500 Hertz. There is a periodicity at 300 Hertz. So we can count them up and count the pulsars maybe.
So you mean in radio or in gamma ray? I mean, the problem in gamma rays is that each of these individual sources is probably giving us somewhere between like the sources that we can identify as possible sources are probably giving us something in the order of 10 photons over 10 years, at which point it's pretty hard to look for periodicity, especially if you think your period is a millisecond. Now, it's actually not quite as crazy as I thought, because I first said this to people, and they were like, no, if you have really good timing accuracy, you need a surprisingly, I mean, Fourier transforms are amazing, you need a surprisingly small number of photons to be able to pull out periodicity. The problem there is actually that there's a correction that you need to make, which depends on the exact position of the source in the sky. And gamma ray telescopes are bad at figuring out exactly where these sources are in the sky. And because there's a significant background, like you can say, okay, I think there's a source here that is contributing 10 photons, but you may be doing it on the basis of, there are 50 photons, I expected there to be 50 photons in this pixel, and actually there are 60. So while you can say that there are probably about 10 photons coming from the extra source, the telling which 10 photons are coming from that source is a much harder problem. And so because of that, to do this, you have to scan through a lot of possibilities for which photons are actually associated with the source, and a lot of possibilities for exactly where the source is centered, and that's extremely computationally expensive. That said, I've been on sabbatical at the Institute for Advanced Study for the last year, and I was talking to some postdocs there who have designed really clever new algorithms for pulsar hunting, and they were saying that, it still seemed, they were saying something along the lines of that if we could have like 200 photons in a pixel, of which we thought that half of them came from the source, like if you can get to that level, then they had an efficient way to rapidly find the location of the pulsar without it being super computationally intensive. There might be a few hotspots in our sample that are that hot. It would only be a few. This would be like thousands or tens of thousands of pulsars, and maybe you have a handful that could be detectable that way. But that's something that we're following up. It might be possible. But yeah, the pulsation search in gamma rays is really hard just because the numbers are so small. But in radio or X-ray, it's much more promising to go after the pulsations. But of course, again, because the problem is the gamma ray angular resolution isn't very good, you don't know exactly where to look. So you have to scan, and that takes time. Or you need a radio telescope or X-ray telescope that has a big enough field of view that you don't need to scan.
You said that dark matter annihilation rate from the center of galaxy, from the gamma ray axis, quite matches what we expect from dark matter canyon.
Yeah.
But to say this, we need the number density at the center of galaxy.
Right. So good. No, that's okay. So that's a really good question. So So the point that you're bringing up is that. Suppose I've got a model which gives me a dark matter annihilation rate, and I say I want the dark matter annihilation rate to be 2 × 10⁻26 centimeters cubed per second, because that would give me the right abundance of dark matter in the present day. But then if I want to convert that to how many gamma rays I see, I need to know how much dark matter there is at the center of the galaxy. And we have pretty good simulations for how dark matter should behave, but the simulations tend to break down when you go to very small scales, both because of resolution issues and because small scales close to the center of the galaxy, there's a giant black hole there, there's a lot of baryonic matter there. It's not obvious how to incorporate all those effects into the simulation. So basically, if here is us at Earth, and here is the galactic center, and I want to look at the dark matter density, then I can have a model that sort of says, oh, the density should do this, but it's probably perfectly consistent with the data for the density to do this, or to do this, or maybe to do this. So then there's a very wide range of possibilities for how much dark matter density I have at the galaxy. Now, that's absolutely true, and it's a really good thing to keep in mind when looking at dark matter constraints from the center of the galaxy. But once you have a signal, you can do a little bit better, because if you assume that the excess is coming from dark matter annihilation, then you've measured the dark matter profile towards the center of the galaxy. You haven't measured the overall normalization, but you've measured the profile. So you can immediately say that, okay, you've measured the dark matter density here, and over near the galaxy, you've measured that the density is falling like that. So then with some offset that you have to work out. So then, there's still an extrapolation. There's still an extrapolation to go, maybe it goes like this versus same slope versus maybe it goes like this. But you have a handle on what this slope is. So if you just assume the power law slope is doesn't change. The power law slope does not change that much over the region we can see, which is about 5,000 light years. If you assume that power law slope stays the same out to the location of the Earth, which is an assumption, we can't validate that. But if you assume it stays the same out to the center of the Earth, you get the thermal relic cross section is what you need. So that's what I mean when I say that it lines up. Because being able to actually measure the slope at the center, you actually have a measurement here and you have a measurement here, and that gives you a much better handle on what's likely to be going on than you usually have, where you just have no idea what the density is towards the center. But there's definitely an uncertainty associated with this because there's nothing fundamental that says the power law slope in R has to stay the same between 8 kiloparsecs and 1.5 kiloparsecs from the center.
So in this sense, you can say something about the focus point.
Yes, so exactly. So if, right, good. Yeah, so if the galactic center accesses dark matter, the Milky Way does not have a core, is the statement, basically. Yes, it has to be, on the other hand, if you're convinced the Milky Way has a core, then you already know the galactic center excess is not dark matter annihilation. So you know, it depends on what your prior is. But yeah, so basically the excess looks like it looks basically like the slope of the density squared. If you assume that it's something spherically, because you can only see it in projection, of course, but if you assume that it's a spherically symmetric object that's been projected, then you find that the density squared is about between -2 to -2 to 2.5. So this gives a density profile that is between about r to the -1 to r to the -1.25. And that continues into regions that are a fraction of a degree away from the galactic center, which is like 10 parsecs. So yes, you can have a few parsec scale core, but the kinds of largish cores that you might worry about, like, would it be a meaningful change to the to the inner regions of the Milky Way galactic halo at the 100 parsec or kpc scales? If this signal was dark matter, then the Milky Way doesn't have a core like that. And if you're sure that it should have a 100 parsec or larger core, then this is not dark matter. So people have very different strengths of priors on what they think that dark matter density is towards the center.
Dark matter has mass, right?
Yep, that's one of the few things we know. It has mass, it has to gravitate, yep.
Are there any hints about the relationship between dark matter and the Higgs boson?
Good. Not a lot, unfortunately. So there are some constraints. Like if the dark matter could scatter, so if you can have the dark matter interacts with the Higgs boson, and then the Higgs boson interacts with standard model particles. So like this could be a proton, for example. If you can have an interaction like this, so a dark matter comes in and exchanges a Higgs boson with the standard model particle and scatters off, there are limits on how strong that interaction can be, because you look for experiments where the dark matter particle could bounce off the protons. So in a lot of dark matter models, where it gets its mass is not predominantly from the Higgs boson. But yeah, I mean, you can write down scenarios where, yeah, I mean, where the dark matter is some. I guess this is partly because I often think about dark matter models where the dark matter is up at the TeV scale or heavier, and so if you want that to get its mass from the Higgs boson, then you need a pretty big Yukawa coupling, which we usually don't want because it usually causes it to be excluded. So I personally have mostly thought about models of dark matter where it doesn't get its mass from a Higgs boson coupling. I mean, but that, yeah, I mean, that is, I guess, like a reason to think that maybe the dark matter is in the same ballpark of mass as the other particles if it got its mass through the same mechanism. The thing is, like, we've searched, so all the particles that we know about except the electrons and the neutrinos and the photon have masses between the sort of GeV to a few hundred GeV scale. And that is the exact region that we've been searching hardest for dark matter for the last few decades for this reason, among others. But, and so far we haven't found anything, which doesn't mean that it's not there. I mean, if the galactic center excess really is dark matter, then is right in this mass range. And you can have scenarios where the dark matter couples to the standard model Higgs sector and get the galactic center excess, right? But yeah, I mean, just in recent years, because we haven't found anything in this range, most theory attention has been on models with mass scales that are that can be very disparate from the standard model. And so usually in those contexts, you think about cases where they get their mass through some other mechanism. But there's a big class of models where you say, suppose that the dark matter interacted with some new particle, and that one of the simplest ways for a new particle to interact with the standard model is to mix with the Higgs boson, if it's a new scalar. And so the Higgs boson could be the portal into the dark sector, and that's what you would expect to happen in a wide range of possible models. But it's one of the blobs on that giant theory plot that I showed earlier. So definitely possible. But and you can get constraints on light dark matter by checking to see if the Higgs boson could be invisibly decaying into it. Like as we get better and measurements of how the Higgs boson is behaving, we'll be able to set better and better constraints on the possibility that the Higgs boson some of the time secretly is produced and then decays away into dark matter particles or something like that. So there are limits on that kind of process from invisible decays of the Higgs, but at the moment we're not really doing precision Higgs physics. Yeah, it's a good question.
These Fermi bubbles align the direction of the jets from the supermassive black hole at the center.
So our supermassive black hole isn't producing jets at the moment. It's extremely quiet at the moment. So the Fermi bubbles are basically aligned well, they're not exactly north and south, they curve a little bit, but broadly speaking, they go north and south. They just go out at right angles to the plane. And that could be true even if they were made by a jet and the jet was at some angle, basically because the density gradient of the gas in the galaxy is close to perpendicular to the plane. So if you start out, there are these hints within the Fermi bubbles. There's kind of a brighter structure in this region of the bubbles, which is sometimes called the cocoon. And there was a very sort of weak hint that maybe there was a jet-like structure extending up into the bubbles, a linear structure extending up into the bubbles this way. It's not highly significant, and some groups find it and some groups don't. So, don't necessarily take it too seriously. But if you take this seriously and you say, okay, maybe there was a jet that sort of went out along this axis, could you get the morphology of the bubbles? You still can for a few different reasons. Like one, the galaxy is rotating, so to some degree, like as this rotates around, it could carve out the bubbles. So, but also because this would be a wimpy little jet that didn't fill the whole bubbles, but there would be a shock wave that expanded out from around it in all directions. And if something like this happens, then how fast and how far the shock wave can expand depends on the density of the gas it's expanding into. So if all the low density gas is up here, it'll expand up like much faster than it can expand sideways. And so that can give you a situation where even if you start out with an angle like this, you sort of end up with something like that. And maybe something that's as apparently symmetric as the bubbles. So yeah, so we don't have strong evidence for an actual jet. But if you want to get this sort of, you want it to not be very strong. Like in other galaxies, we see jets that basically look like this. So they're extremely collimated. They come out the emission comes out in almost straight lines, and they go for hundreds of thousands of light years in some cases. The Fermi bubbles are not nearly that big, and they're not nearly that straight. Like they're these puffy structures. So if you want to make them with a jet, the jet can't have done all the work. It has to have just gotten things started, and then there was some expansion out from around the jet. And there was a question up there. Yeah.
But is the possibility that the dark matter annihilation can act as a possible source of ionization?
Great question.
And if so, then can the fluctuations in Lyman alpha forest can act as a template to this dark matter annihilation?
Okay, yeah, so the question was like, what's the possibility that dark matter annihilation can affect reionization? And so I actually wrote a paper on this a few years ago, so this is a topic near and dear to my heart. So the probability so the first question we wanted to test a few years ago, so I told you that when the universe was a few 100,000 years old, it went from being almost totally ionized to being almost totally neutral. Well, it then went back from being almost totally neutral to almost totally ionized when it was a few 100 million years old in the epoch of reionization. So now dark matter annihilation could produce ionizing particles as well as heat. And so a question you might ask is, as you just asked, is how big a role could dark matter play in this reionization process? Unfortunately, it turns out that it's actually pretty hard to have dark matter annihilation play a really big role in reionization. And the zeroth order reason is that if you're producing enough ionizing particles to reionize the universe at redshift 10 when it was a few 100 million years old, you tend to also have been producing ionizing particles for quite a long time throughout the cosmic dark ages, and at a high enough rate that you would have ionized a small but visible fraction of the hydrogen at earlier times. So basically, the situation here is that the cosmic microwave background experiments, those photons fly to us through the cosmic dark ages, through the epoch of time when the universe was neutral. If you make it less neutral, if you allow some of the hydrogen to be ionized during that epoch, then those free electrons and free ions serve as scattering sites for the photons of the CMB, and they modify the pattern on the sky that we see. Now, down at redshift 10, you can add quite a lot of ionization without being excluded. I mean, because we go through reionization and we don't have very tight limits from the CMB on exactly how that reionization occurred. But at redshift 500 or 600, if you ionize even one hydrogen atom in every 1,000, you can see the effects in the CMB. Like, it has measurable visible effects on the CMB anisotropies, which can be disentangled from what's happening at late times. So because of that, it turns out it's basically impossible, as far as I know, to have a situation where dark matter did 50% of the work during reionization, because in any dark matter model where you ionized 50% of the hydrogen during reionization, you would ionize more than 10 to the minus 3 of the hydrogen at redshift 500 or 600. So that's not quite true. There are dark matter models where that statement I just made is not true, but they tend to be models where the signal gets much brighter at late times and in big galaxies, and in those models, you would see the signal in our galaxy before you saw it in reionization. So you sort of get to peg the signal from two directions, from redshift 600 when the universe was very smooth and uniform, and the present day when the universe is more inhomogeneous and has bigger galaxies than it did during reionization. And that allows you to basically kill the possibility that it does more than about 10 or 20% of the ionization. But it is possible for dark matter to. You're about to tell us that we should go out to the barbecue?
I was just going to say that you can have P-wave non-thermal.
You can have P-wave non-thermal, but even then, I think the present day constraints on indirect detection of P-wave are strong enough that, I mean, that saves you from the CMB constraints, but I think you still find that it's hard to do more than about 10% of the ionization, is my memory of how this worked out. But yeah, it's better for S-wave. For S-wave, it's hard to do more than about 0.1% of the ionization because the CMB limits are so strong. But you could have dark matter scenarios that ionize 10% of the universe during reionization. And so if that was true, then as we get better constraints on the reionization epoch, as we get better limits from Lyman alpha or from 21 centimeter surveys, we may be able to use that to put tighter constraints on that kind of model.
But if it annihilates before the recombination,
yeah.
So it will create also it will destroy the equilibrium. So there will be a black body radiation in black body spectrum also, right?
Good, yeah, good. So the question is, so what happens to the CMB black body spectrum? That is also a viable signal, but unfortunately at the moment, the signal in the black body expected from annihilation is about 4 orders of magnitude below what we can see. Sorry? Yeah, below the Kobe limit. So it's like 10 to the minus 9, 10 to the minus 10 is an absolute distortion. So the reason for that is actually that, so if we look at the level of ionization, so to ionize one hydrogen atom costs only 10 to the minus 8 of the total mass energy stored in the hydrogen atom. But so you can, and there's 5 times as much dark matter in mass as there is visible matter. So if you take 1 part in 10 to the 9 of the mass energy stored in dark matter, then that's enough to ionize everything in the universe to a good approximation. Because the kinetic energy is also really small, it's enough to heat up the whole universe by order 1 factors. But if you ask, okay, I take 10 to the minus 9 of the energy density in the matter and convert it into radiation at, say, the CMB epoch, this is pretty close to matter radiation equality. The energy densities in matter and radiation are somewhat similar. So 10 to the minus 9 of the matter density is 10 to the minus 9 of the radiation density, and then you just don't get a big signal. But yeah, but future CMB spectral distortion experiments might be able to look for this, but at the moment it's not a competitive constraint. Yeah, so if Pixie was funded and flew, then it would start to get close to being able to see this. Yeah, you're welcome. No, great questions.
All right,
okay.
If there are any other questions, let's thank the speaker.